Okay, so welcome to this fifth video in linear programming. In the previous video, we developed some notation that's going to help us solve this system of equations ax equals b. Once we solve ax equals b, assuming that a solution exists, we're going to make sure that it's non-negative, and then amongst all such possible solutions, we want the one that maximizes c transpose x, and that'll solve our linear program. But to do all that, we need to start at the beginning and first just solve this system of equations ax equals b, which is what we want to do. And not just solve it, but solve it in a convenient way. This matrix A is the same matrix from last time. We're going to keep referring to this as an example. To the end of solving this in a useful way, we first started indexing our columns from 1 to 6, because the column space became an important vector space to consider. And so we indexed the columns from 1 to n, in this case n equaled 6, and we said take a subset of the indices, and we say that that's a basis if the columns that it indexes, if those form a basis of the column space of A, which is what I've just said here. So for example, B equals the indices 1, 5, and 6 was a basis because the columns, the first, fifth, and sixth columns are a basis for the column space of A. So then we say the indices 1, 5, and 6 themselves are a basis. This is what we're going to say from now on, that the set of indices is a basis. And then the non-basic indices were all the other indices, so the complement of B inside all the indices from 1 to n. And so that was all from last time. Finally, we developed some notation. We used some notation AB and XB, and AN and XN. We were able to rewrite A times X as this. And this was our new notation. AB, for instance, is the submatrix of A indexed by the columns of B. And XB is the subvector of X indexed by B, and analogously for the N's over here. Anyway, so this was just a rearrangement of the columns. We put the ones that were indexed by B on all together, and then we put the ones that were indexed by N all together. And we separated them like this, and we showed that that was true. Now in this video, we would actually like to carry on with this and actually solve ax equals b in a convenient way. And so to that end, we're going to make a definition. So we're going to start now with the definition. So so a vector, we'll say a vector x bar is a basic solution of ax equals b for the basis b, capital B, if two conditions hold. Before I write them down, so x bar is going to be something that we're calling a basic solution to the system of equations ax equals b, and basic solutions is the topic of this video, in fact. So first we need to say what it is. So what is a basic solution? If it's a basic solution if the following two conditions hold. First, if it solves the system, if ax bar equals b. So that has to be true. The second thing that we want to be true is for x bar sub n to equal 0. So that is the subvector of x bar indexed by the indices of n is the 0 vector. Just so we're comfortable with this notation, we can rewrite this and say, in other words, x sub j equals 0 for all indices j in the non-basic indices. So note that this is with respect to a given basis. So once we've chosen a basis b, then we can find a basic solution, assuming one exists. We haven't actually showed how to find it yet, but we will momentarily. So it's, if we want a solution, it's kind of obvious that we want it to solve ax equals b, so it's obvious that we would want the first condition to hold. The second condition is a bit more surprising, but in light of what we're going to discuss in this video, it will not be surprising much longer. So first, let's just take note of the fact that since B is a basis, then if ax equals b has a solution, then we only need the basic indices to create a solution. In other words, we don't need the non-basic indices because the basis b spans the column space. So for example, if we take a look at this matrix A here, the column space is what is spanned by all 6 columns. But in fact, since B being the first, fifth, and sixth columns is a basis, the column space is also spanned by the first, fifth, and sixth columns. And we don't need the second, third, and fourth columns at all. And so if ax equals b has a solution, then it will have a solution where the second, third, and fourth components, the non-basic components, are all zeros because we don't need them. There is a linear combination using only the basic columns that will give us a solution precisely because the first, fifth, and sixth columns form a basis of the column space. So that's why it's a natural thing actually to have this second condition. So let's take a look at what happens. So if x bar exists, so if x bar is a basic solution, let's say we've already gotten our basis b for our system of equations ax equals b. So then if x bar is a basic solution, what that means is these two conditions hold. Then what happens is we have a times x bar. Well, from the previous video, it equals this. We can just separate everything out. It's ab x bar b plus an x bar n. But of course, ab x bar b plus an x bar n, we just said, by definition of being a basic solution, x bar n is the 0 vector. So this is this becomes the 0 vector, and so this just becomes ab xb, x bar b. Oh, sorry, there we go. ab x bar b. So this 0 makes this the n part vanish, and the b part is the only part that remains. Okay, and so let's just keep working up here. And at the end, we know that by condition 1, it's a solution, so it also solves the system. So maybe before sorry, let me go back down here just for one more moment. This equals lowercase b, the vector b that solves, or that is the right-hand side of this linear matrix constraints. Okay, so what we have is that ab x bar b equals b. So now, how do we solve this? Well, the thing that you need to realize is that actually this matrix A sub b is invertible. So this matrix that I've just circled is invertible, and that's because what is AB? It's the submatrix of A that consists of the columns of B, indexed by B, and those columns form a basis, and so that this is going to be a square matrix, and it's also all those columns are going to be linearly independent. And so when a matrix consists of, it's a square matrix where all the columns are linearly independent, then it's invertible. And so therefore the inverse of this matrix exists. And so we can multiply on the left and right. And so what we get is that x bar b equals AB inverse times b. You can see, for instance, in this example that we have, our matrix AB is the first, fifth, and sixth columns, and they form a basis, and so therefore they're linearly independent, and therefore it's invertible. And so what actually that also shows is that this is unique. This x bar b is unique because we solved it uniquely. It's AB inverse times b. So given the basis b, this x bar b is unique. And in fact, the overall solution x bar is unique because we already know what x bar sub n is. It's 0. So x bar is also unique because it's the components indexed by b along with the components indexed by n, but all the components indexed by n are zeros. And so we just know how to fill that in, the rest of those indices, and automatically they're all zeros. Okay, so given a basis b, so let's just write this down then. Given the basis b, the basic solution x bar is unique if it exists. So how can we find this x bar b? Well, but before we do this in general, let's just take a look at how this works out in a given example here. So I'll use this space down here. For example, let's just see what it works out to be in this case. So if this is our matrix A, and we have AX equals B, where the vector B is, let's say, that it equals 2, 1, 1. Is that legible? I should make that just slightly bigger. It's 2, 1, 1. Anyways, you can hear what I'm saying, even if you can't see it. But yeah, that's visible now. Okay, so we have this matrix A times the vector x equals 2, 1, 1. Now, does this have a solution? And the answer will be yes. And that's because we have a basis. The basis 1, 5, 6. So I'm going to work over here. So AB equals 2, 1, 3 is the first column. We're using this basis here, 1, 5, 6. So the fifth column is 0, 1, 0. So I'll write that here. And the sixth column is 0, 0, 1. And so that's what the matrix AB is. And so now we already know that x bar sub b, the basic solution, is going to be AB inverse times lowercase b. So it's going to be 2, 1, 3, 0, 1, 0, 0, 0, 1 inverse times the vector 2, 1, 1. And we know without even having to check that this matrix is invertible because it consists of linearly independent columns. And so it will be a square matrix, and those columns will be linearly independent, and so therefore that matrix will be invertible. And so this all exists and is well defined, and so if you work this out, we know how to work this out from linear algebra. If you work it out, it's 1, 0, minus 2. And what you can see is that if you take the linear combination 1 of this, 0 of this, and minus 2 of this, you do get 2, 1, 1, because we get 2, 1, 3, and then 0 of this contributes, and then minus 2 of this contributes, but there's only one non-zero entry here, which is this, so minus 2 times, so this minus 2 times this vector, this component becomes minus 2, so it becomes 3 minus 2 is 1, and the rest are all zeros, so it stays the same, so it's 2, 1, and 3 minus 2 is 1, so we get 2, 1, 1, which is our solution. And so that's how that works. Now it's worth noting that the overall solution here, we got x sub b is 1, 0, minus 2. The overall solution is x bar equals, the first component was this 1 here. The second, third, and fourth components, the non-basic components, were all zeros, because this is the basic solution. So 0, 0, 0. And then there's two more components. The fifth component was this 0, and the last component is minus 2. And so that's the overall basic solution x bar. But notice that this is not non-negative. It does not satisfy the non-negativity constraint precisely because the last component, the sixth component, is negative. Therefore, we haven't actually solved the overall system yet. We're going to, if we had, this would have been called a basic feasible solution. As it is, it's just called a basic solution. But we could have added the word feasible onto it if it would have solved all the constraints, but it did not. We're going to show in subsequent videos how to fix this situation. That will be the subsequent topic, though. The last point to mention in this video is that I asserted that this matrix A sub b is always going to be square. If it is square, then because the columns form a basis, it will be invertible. But why does it have to be square in the first place? For instance, had I added on an extra row of zeros, let's say, to this matrix A originally, then the indices 1, 5, and 6 would still form a basis of the column space. And the column space would be formally speaking, it would be different, but because there's it's four-dimensional now, but the final component is always a 0. But anyways, 1, 5, 6 would still be a basis, but there'd be three basic vectors, but they'd be in R4 rather than R3 now, and so when we write down the matrix A sub b, it would not be square. It'd be 3 columns and 4 rows. And so that wouldn't have worked. So why? So at face value, this what I said was not true. But what we can say is, without loss of generality, that it will be true. If we have more, if the dimension of the column space, if the dimension of the column space, which would in this case be 3-dimensional. If that is less than the number of rows, then that must mean that the rows, there's some linear dependence amongst the rows. And that's from linear algebra. And that's because there's this notion of rank of a matrix. And the rank of a matrix is the dimension of both the row space and the column space. And what we're saying is that the row space and column space of a matrix always have equal dimension. So the fact that this was a 3-dimensional column space means that the matrix A also had a 3-dimensional row space. But there's 4 rows in this, now that I've added on this row of zeros. So there must be some linear dependence amongst these rows. And so therefore we could eliminate one of the rows without affecting the constraints at all, because it's a redundant constraint. It would not change the feasibility of the constraints because of the matrix being having redundant rows itself. In this case, it's obvious what the redundancy is. It's this row of zeros that we've just artificially added on. But more generally, it might be less obvious what the redundancy is. But in principle, some redundancy must exist if there's more rows, if the dimension of the column space is less than the number of rows. So without loss of generality, we can just assume that we started with non-redundant rows, because if we did have redundant rows, let's just eliminate some redundancies until we don't have any more, and then start working from there. So let's just, right out of the gate, just assume, without loss of generality, that the number of that the rows of the matrix are not redundant. In other words, the matrix as full row rank. In other words, the rank of the matrix is equal to the number of rows, and so therefore also the rank of the matrix is equal to the number of columns in the column space. In a basis of the column space. And for that reason, the submatrix A sub B is always going to be square, and so we can then conclude that it's always going to be invertible as well, because the columns will be linearly independent. And so that's why all this works, and that if we're given a basis, so we can erase these zeros now. So if we're given a basis B, then if a basic solution exists, then it's unique. It could be the case that AX equals B has no solution at all. But if it does have a solution, then it has a basic solution. And given a basis B, there's a unique basic solution. Okay, and so from this point, we're going to be able to start manipulating our basic solutions to obtain a basic feasible solution, should it exist. Otherwise, we'll determine that one does not exist, and we can conclude that our linear program has no solutions at all. But otherwise, we'll find a basic feasible solution, and then from there, we'll be able to maximize our linear program. But that's all in the future. That's the end of this video. We just wanted to show that given a basis B, if AX equals B has a solution, then it has a unique solution for a given basis B. A unique basic solution for a given basis B. And that's it for this video. So thanks for watching.